Good morning, everyone. We were discussing about production of phosphoric acid, and we went through the process. Just to give you an idea of what are the requirements, like to make 1 ton of phosphoric acid with about 90% yield, you can see that you require about 2.5 tons of phosphate rock. Over here, you have 32% as the P2O5 content in the rock, and you can work out, what it means in terms of how much phosphoric acid theoretically you'll get from this, and then how does it compare. This is the requirement of sulfuric acid, and as we discussed that when you produce uh, phosphoric acid, you also obtain phosphogypsum, which is nothing but gypsum, but because it's from the phosphoric acid process, therefore it's called as phosphogypsum. There are precautions that one needs to use to basically use this because it is radioactive. There is radioactivity in the rock phosphate, and some of it is passed on to the gypsum. And so, it is not routinely something that is used. I remember there used to be a company which had a mountain of this stuff outside their factory, and they were looking for people to help them to make use of it. But there's a serious problem because of that. Now, the second thing that you would have noticed, and I told you when we talked about the rock phosphate compositions from different places, is that all rock phosphate except for chlorapatite, which is very sparse, its availability, it has about 3 to 4% of fluoride. And so the ideal thing is that the fluorine should be removed from the phosphoric acid before you produce fertilizer, because otherwise the fluoride will remain. Now, the process, which one of the processes, I mean, this is not the only thing, which is followed, is that you would have seen that most of these rock phosphates also have some amount of silica. You may have to add some silica additionally from outside, but this is for phosphoric acid. So, once you've got the phosphoric acid, you can add some silica to it. Then what that silica does is that at high temperatures, it reacts with the fluoride and it forms H2SiF6, hexafluorosilicic acid. So what you then do is that and do it at a fairly high temperature so that the H2SiF6 can boil over. Okay, and so you separately collect it. I'm not going through the entire details. Okay, and then from here you can get a phosphoric acid which is free of any fluorine. In fact, it works quite well, and you can remove about 98% of the fluoride in this manner, provided you do it. Obviously, it's another operation downstream that one needs to carry out. So, at the heart of it is that you have to strip off the H2SiF6, which is formed when you react it with silica, the phosphoric acid, and then really you can recover the H2SiF6. Now, the H2SiF6 has a very limited use. Earlier, it was used a bit more to make aluminium fluoride for the production of aluminium, for production of cryolite. You would have seen how ALF3 is used. Okay, but what has happened is that the quality of ALF3 that you get in terms of a density requirement is a bit low, and so people don't really like it that much. The other application used to be for fluoridation of water. Drinking water earlier used to be fluoridated because you need a minimum amount of fluorine in the water for our body, for healthy gums and things like that. So it used to be a standard practice to fluorinate the water, and a few other synthesis which you can do with H2SiF6. But the production of rock phosphate and phosphoric acid is so large And then if you look at the amount of H2SiF6 which will form, considering that there is 3 to 4% of fluorine, is a huge amount. And so that is the reason why a lot of people have coolly been leaving the fluoride in the phosphoric acid, and they're not recovering it. And this company, Bus, in Switzerland, they did some extraordinary work. Fluorine is a very important reagent, in organic synthesis. Starting from your Teflon to so many things are fluorine. Many of the drugs, very important drugs, have some substituent of fluorine. But the refrigerants, it's another huge area. There's no end to the number of fluorinated molecules. So in a way, you need fluorine, but the problem was that most of the people who work with fluorine uh, usually will work with anhydrous hydrofluoric acid, HF, and that they have been producing from fluorspar, which is calcium fluoride. So India imports a huge amount of fluorspar, maybe about 120 lakh tons of this, and then basically you react it with sulfuric acid, you'll get gypsum from that, and you'll get anhydrous HF. And that HF is the one that is used to make all these. There are there's some work where you can use other kinds of fluorinating agents, including fluorine F2, which is obtained by electrolysis. Like you can take sodium chloride, electrolyze it, and you'll get fluorine, and a few others like potassium fluoride is quite a popular fluorinating agent. But the bulk of it is really from the anhydrous hydrofluoric acid, HF. So what this company has done is that they have been able to take H2SiF6. I mean, it is like solvate. The chemistry was known many years back. There's nothing new in the chemistry. But what they've done is really a very important engineering, which has made it a practical process. And the first two plants, or three plants, I think now, have been installed in China, typically around 10 to 20,000 ton capacity of HF. This is really important because you can use the byproduct from the rock phosphate phosphoric acid process to make the HF rather than, and the fluoride is already mobilized. So obviously it would make much more sense to use that rather than again mining fresh fluorspar and making anhydrous HF. So I consider this one of the very important developments from the viewpoint of sustainability, and I'm pretty sure that in the years to come, many more of these kinds of plants will be set up. Now, why is it important? And especially for India, because we are very big in organic synthesis, and we make a lot of fluorinated molecules. In fact, the person who helped me prepare this slide is someone who works in the fluorine industry. So, he knows what exactly are the issues at hand. It's important because the H2SiF6 is being neglected. It didn't have enough market, and therefore, as I told you, people were not removing the fluorine. Just see what is the fate. This is a study that was done by ICT by us in 2018. This is the paper that made people aware of how serious the problem is. These are all DAP fertilizers, diammonium phosphate. I'm talking about 2016, then 2019, some more samples were collected. This year, some more samples have been collected. Some are yet to be analyzed. What you can see is that barring one or two exceptions, most of them have fluoride close to about 1% by weight. So there is one that we found now which is almost 2% by weight. I mean, it's just unbelievable. And this stuff is, once it goes into the field, there's no way to take out the fluoride after you have applied it, right? I mean, how will you remove it? And so what people have been doing, obviously it is going to not only get into your food chain, but it will also contaminate the groundwater. And in India, we have probably one of the most serious problems of fluorine in our groundwater. And all these people, everybody has been trying to pass on the buck to a natural cause. They were talking about geogenic causes, and this happens, that happens. I mean, maybe some of those things happen, but the point is, does the fertilizer contribute to the problem or not? And it clearly does. So if you look at, that we consume something like about 10 or 11 million tons of diammonium phosphate, and you multiply with 1%, you will find out how much of fluoride you are adding into the soil. So it's a huge problem. I hope that some of you, if you ever get into these areas, will look at it carefully. And this is what happens, that if you don't take a holistic view of a solution, if you're a fertilizer guy and you don't care two hoots about anything else, and we have fertilizer specifications which do not mandate anything about impurities. It only tells you about how much nitrogen there should be, how much phosphorus there should be, how much potassium there should be. But it doesn't tell you that what is the maximum tolerable amount of fluoride that you should have. People have been merrily taking advantage of that. So obviously, industrial processes are also to some extent linked to issues like sustainability, linked to issues like planning and policy, and that's what someone has to do. One has to put it all together and then try to see what is the best solution to the problem.
So I had a small doubt, sir.
Yeah, yeah,
So in the first process that you covered today,
yeah.
so is the temperature high inherently?
When you are making phosphoric acid, the temperature will be around, as we saw, it would be about 110 degrees centigrade for the hemihydrate process. So if you are to integrate it, that means, yes, you straight away take it after filtration and you take it for fluoride removal, then it would inherently have a high temperature. But
So
if you
but
don't have that, then of course you have to heat.
but I have a small doubt. Yesterday while giving the reaction,
Yeah,
you said that calcium phosphate with sulfuric acid will give gypsum like CaSO4 in the form of 0.2 H2O.
yeah,
So but then why?
0.5 H2O.
So, but then why not convert this into the hemihydride, like adjust the temperature such that hemihydrate is formed? Because
Which
because
one?
then so this
No, no,
reactions.
no. This is downstream. This is after you have made phosphoric acid. Okay, you're starting with phosphoric acid. This is a add-on downstream.
Okay, okay,
All right. Huh?
yes, sir.
So, so this is the reality. In fact, recently, I mean, about a year back, we looked at, once you have made the fertilizer, there's no point talking about phosphoric acid and fluoride removal because you've already made it. The question is, if you have already made it, you have got this. I mean, should it just be allowed to be used in the field, or should there at least be a fallback option where you might be able to remove it even after you have made a fertilizer? So a thermal treatment process has been developed. All the fertilizers don't seem to work, but the majority do, where you can thermally treat it, like in a rotary calciner would be an ideal way to do it. And you can just, while it's in the solid state itself, you can remove the fluoride. So this is an important development. It's just been published this year, but it's very, very important that we don't just throw up our hands and say, what can we do? And since we are importing so much of fertilizer and you have no control, then you have to do it in India. You must take care of it. And don't forget that we have the second largest agricultural base. So our situation is not like Europe or countries there, which are small population. Look at our population. Look at how much fertilizer has to be applied, and look at the gravity of the problem. So it's a very serious issue. Now, if that were not enough, let me also show you what has been found since around 2016. This is yet not published, but it's just been patented. You have seen that the rock phosphate has a lot of uranium. So I had asked BRC whether they can analyze for uranium in the fertilizers. This is around 2016. So we provided them some fertilizer. Some of them which you see is less because single superphosphate has less amount of P2O5, and the uranium is coming from the rock phosphate, and so it will be proportional to the amount of P2O5 that you have in your fertilizer. That's the reason. Whereas DAP has roughly about 3 times the amount of P2O5, and that will explain. Like 50, if you multiply it by 3, it will be about 150. So it's not less. Proportionately, they are about the same, and that's why the DAP fertilizers have higher concentrations. Now, because it's such a serious issue, it was analyzed by 3 different agencies. I sent it to each one, and these were blind tests because one had to be sure that the analytical techniques are convergent, that they give you at least to some extent a comparable number. And some of the analysis was also done by ONGC. So you can see like there was reasonable convergence of numbers in most of the cases, not in all cases, but reasonable convergence. Then there were samples which were analyzed again from 2019. Again, I mean, some of them had extremely high levels of uranium, but there was also one sample which there was no uranium. Now this happened to be from RCF when they were producing phosphoric acid and making fertilizer, and they had a tie-up with BRC, so maybe they have set up a plant to remove uranium. But it's not true now because they've stopped making phosphoric acid. They're just buying things. So the situation may be very different now. Now, and you can see, I mean, again this year, 2 samples were analyzed. Another 8 are awaiting analysis. Consistently high results: 180 milligram per kg, 178 milligram per kg. Yesterday's lecture, you would have seen that we consume about 11.911 million tons of DAP in 2020-2021. DAP is not the only fertilizer. We have consumed many other things. I'm just focusing on DAP just so that you can understand. And now, if when you can multiply it, okay, that if 150 milligram per kg is what is the average content, and you have got 11.91 billion tons of DAP being consumed, this alone, the DAP alone, it means that you are actually putting in our agricultural fields, not you, we are, 1810 tons of uranium. How much does 1810 tons of uranium amount to? I mean, is it a high figure, low figure? Well, the drinking water standard says that uranium content should not exceed 3 ppb, 3 parts per billion. When you see that, and surely some of this uranium will go into our groundwater, it's surely going to contaminate. I mean, there are, everybody has been playing games. Like in Punjab, for example, there's huge number of cases of cancer in some of the regions, especially very agriculture intensive regions. People have been talking about all kinds of causes. I'm sure this uranium has got something to do with it. How can it not have something to do with it? That's why it was analyzed so responsibly by 3 different agencies, just to be sure that these are not artifacts, these are real numbers. Now, this number of 1810 tons, just to tell you that in India, all the nuclear power plants that we have today, including the ones which are under construction, the total amount of uranium, natural grade uranium, which is not enriched uranium, natural grade, which has only about 0.7% of uranium-235. Our requirement is around around 2000 tons. So you can actually meet the entire requirement of the nuclear fuel industry in India if we recover the uranium from the fertilizer, or better still, if we can recover it from the phosphoric acid. Why from the phosphoric acid? Because there are very well-known methods which have been established over the years. Since 1950s, I mean, the US was the pioneer, since late 40s, they were developing it, and they were, of course, developing it for making weapons at that time. So all the focus was on making nuclear weapons, and so they needed a lot of uranium. Much later, of course, the use in nuclear power plants came into play, and the US is quite big in it. And a country like France generates 72% of its power from nuclear energy. Right? By comparison, in India, we have something like 3% generation. So these techniques had been well worked out. One is that there is a technique to precipitate out the uranium. Another is you can do a solvent extraction with some organic organophosphorus solvents, and you can pull out the uranium from the phosphoric acid, and then you can again strip off the uranium which you pull out, and then you can recycle that solvent. And another is that you can take a resin. It's an amine impregnated resin which is very selective for binding of uranium. So you can do an ion exchange and remove the uranium. So the methods exist. Now, just like in the case of the fluorine, what happened is, people found that it's easier to produce HF from calcium fluoride, and nobody was putting a leash on them and preventing that from happening. So here again, the guys who are into nuclear energy, they have been merrily importing uranium-rich ore from Kazakhstan and producing the uranium required for nuclear power, and letting all this uranium go into the field. It's so irresponsible. But just to tell you that it is not as if people were not aware of this. That uranium is present in fertilizers is something that has been known. We are not the discoverers of that. That was actually has been studied by many people. And in Germany, what they have done is, I don't know whether it's been finally implemented, but they had suggested that if you have more than 20 milligram uranium per kilogram P2O5, in terms of per kilogram P2O5, this value will be close to about 300. That's the average level that we have. So that if it is more than 20, that there should be a mandatory labeling on the fertilizer which says that it has more than 20 milligram uranium per kg P2O5. And what they further said is that if it is more than 50, then it is not negotiable. You cannot sell it, which means that you either recover that uranium from phosphoric acid, or if you have not done that, then you better take it out from the fertilizer which you have made, which is off spec. But nobody will allow you to put things in the field which have more uranium than this. And because again, just like fluoride, it's quite straightforward to remove the uranium from the phosphoric acid, but people are not doing it, as I told you, and you have seen the data. And so you are compelled then to look at a method by which uranium can be taken out from the fertilizer itself. That has been done. There are certain drawbacks. It's not all happy news. There is some good news and some things which are not so good about the process. But a patent application has been filed, and one will have to see if it's possible to overcome those drawbacks. Like there is some loss of phosphorus, during the process, and which nobody is going to accept. So one will have to see whether that problem can be solved. Okay, so a huge problem. So it's not just about making these fertilizers. It's about making the fertilizers responsibly. And today, because we do not have our own feedstock and you're importing things, you are so vulnerable. One will have to check with those people what they're giving you. They might be poisoning our country. So that's the kind of issue that you need to look at. What I've taught you till yesterday is what is known as the wet process phosphoric acid. Why wet process? Because we are using sulfuric acid and recovering phosphoric acid. Now, we know that phosphorus has many other applications. So, for example, the greatest application of phosphorus earlier was basically in making a matchbox. The striking surface in a matchbox is made of red phosphorus, whereas the matchsticks have sulfur compounds, and it's all a question of that minimum friction is what causes the whole thing to ignite, because these are extremely flammable materials, phosphorus and sulfur. So there was always a need for phosphorus, and you cannot get phosphorus by that method of phosphoric acid. To convert phosphoric acid again into phosphorus is extremely hard. So people had to devise a different method, a dry method of producing phosphorus. Where else was it important? Like, for example, you can react phosphorus with chlorine and you make things like PCl3, POCl3, which are really the starting points for to make all kinds of organophosphorus compounds, including those which are used for uranium extraction. Phosphorus chemistry is huge in organic chemistry. Another is that, as I said last time, that phosphorus pentoxide is used as an acid catalyst in many reactions. It is used as a drying agent, okay, P2O5. So huge applications. And again, you see, there are applications where you may require an extremely pure phosphoric acid, which you may not be able to get from your wet process, or you'll be able to get, but with a lot of steps, operations involved. So all of those actually were the motivation behind development of a alternative technique for recovering phosphorus. The technique is really thermal. So what you do is, this is your rock phosphate, I mean the principal constituent, calcium phosphate. And just like, we have seen for so many compounds which are oxides and things like that, if you heat them up with carbon, you can recover the element and you generate carbon monoxide. So it's not very different here. You can heat calcium phosphate with coke. One adds some silica as well into this. Can anyone tell me why silica is added? It's a stoichiometric amount.
Will form slag.
Yes, got it. Calcium silicate forms molten slag. Okay, and so your furnace is just getting emptied out. You're putting it in, it's reacting. The phosphorus is volatilizing. The boiling point of phosphorus is around 218 degree or something of that sort. We'll put P boils, vaporizes 280 C. Now, what is the temperature that you require? I'll show you. It's a very high temperature that you need for this process. Okay? So, under those conditions, the slag will just drain off from the furnace. The phosphorus will come out as vapor. Okay, and so I can keep continuously feeding more and more of the phosphate rock and your carbon and everything, and the process goes on. You can have a continuous operation of your furnace. That's what you do in this chemistry, and then it initially forms yellow phosphorus, which has to be converted into the more flammable red phosphorus. What you have in your striking head of the matchbox is red phosphorus. And then, of course, if you can burn the phosphorus in oxygen, you'll get P2O5, from which I can make phosphoric acid of a very pure quality. Or I can react the phosphorus, as I told you, with chlorine, and I can make PCl3. So it's extremely powerful, once you make phosphorus. This, I believe, is probably the first patent on the manufacture of phosphorus, which taught how to make this whole process roughly that I schematically told you. These are the people who for the first time were able to actually do it. You can see, I prefer to use solid carbonaceous matter such as coal or coke to produce this reducing action. So that's at the heart of it. Now, this thing is done in this particular reactor, and so I will show you step by step what is the process. So you are taking phosphate rock, which has about, like in India, it has about 30% of P2O5, or you might import it, and then you grind it up as you have to do for making phosphoric acid also. You grind it up, okay? And then you add coke, right, which is your reducing agent, because the coke and the phosphate have got to be intimately mixed, because it has to reduce the phosphorus. So what you have to do is you have to put them together and then sinter it, so that this compaction makes the carbon and the reducing environment available to the phosphorus. And then you put in air. You need this air to partly burn the coke so that you can increase its temperature to cause the sintering. Otherwise, you won't get sintering. So it's a high temperature sintering. That's why you need some combustion to generate the heat. Then what you do is that there'll still be some fines. So you do a screening, and the fines you just recycle, put it back over here, and then again it will get sintered. And then this stuff is basically put into a mixer where you put your sand, that silica. And you also need now coke. The coke is required now for the reducing action. Here the coke was primarily required for the heating action, to heat it up so that you get a good sintering of the material. And after that, you put additional amount of coke along with sand over here. And this is your electric arc furnace, which was invented by Henry Moissan. Of course, you need this power. You need 250 to 300 volt line. And this consumes a huge amount of power. And I'll show you. Why? Because the temperature in this zone, in the fusion zone, is 1400 degrees centigrade. 1400 degrees centigrade, you cannot get it by just burning coal and things like that, or natural gas, or even oxyacetylene flame. Only an electric arc furnace will give you that kind of a temperature over here. Now, as the reaction is taking place, which reaction? The reaction, oh, you've seen the reaction. So you know that it forms phosphorus and carbon monoxide and slag. So that slag, basically you're draining out, and you're cooling it just so that, after that it can be disposed. In fact, this is where ingenuity sometimes comes in. There is a lot of applications of slag for making, for example, these vitrified tiles. You can make tiles out of the slag. Now, to make tile, you need enormous amount of heat. You have to increase the temperature to make tiles. It's done at a very high temperature. Now, it's so silly to let this thing cool and to form a solid and then dispose it somewhere and all. If, for example, it could be integrated with tiles manufacture, straight away take the molten slag and put whatever you have to do and make your tile. That is the kind of novelty and ingenuity which you will be required. And those are the kinds of thinking everywhere with your knowledge of chemical engineering. Always ask, I don't want to let go of a single joule of heat. So, what can I do with the hot stuff? That's the way you should think. And then, of course, other applications like it's used in road construction, some other things. Of course, where you need to cool it down, for using in roads, etc., you go ahead and do it. Or it might be cooled to a certain extent and you put it along with bitumen and then you make the road. So there are various things that you can look at. Only thing is, one has to always look at the logistics because these things have got to be adjoining each other. I mean, you can't transport the hot stuff 100 kilometers away. It has to be somewhere there. Now, then from the top, your P4 is coming out, the vapors. It's over here to 80.5 degrees centigrade, the boiling point. Now, because there can always be in these situations some amount of fines that can get generated. So, what you need to do is that you need to settle down all the fines and just have a pure gas phase. So, that is done with the help of a electrostatic precipitator. Most of colloidal substances are charged, so they tend to settle down when you do an electrostatic precipitation. And then what you do is it's hot. Of course, it's coming out around 1400 degree. So what one does over here is that one sprays water on the gas mixture. Now, what else is there? There is CO, which will be formed. There will be CO2, some amount of maybe even all this HF and stuff like that might be present, right, in this. So some of the things will not be soluble in water and those things will escape, predominantly CO, because then the CO is actually used as a fuel for making syngas. Because I've got CO, I can do the water gas shift reaction and I can generate hydrogen to also. And so I can generate syngas, okay, from this. The P4 fortunately is not reactive to water. So you can store phosphorus, this yellow phosphorus, underwater. And of course, as soon as you put water, it will also solidify the phosphorus. So that phosphorus is coming here. Now there is a process that is known to convert yellow phosphorus to red phosphorus, which I'm not going into. This is the one which is used more extensively, the red phosphorus. Now, what you can also do is that I need not spray it with water. I can take the hot stuff which is coming out and I directly put it into a combustor. And so I put in air for that. Okay. And what will I form? I'll form P2O5. And then you can add water. And this P2O5, well, again, there might be some fines. So you have another electrostatic precipitator here and let go the carbon dioxide in a clear gas form. And what you can also do is that you can see, because I'm working now with P2O5, I can actually make extremely concentrated phosphoric acid, 85%. You remember we could barely touch 50 to 60% with the wet process. So obviously the cost of making concentrated acid from a dilute acid can be circumvented in this process. But the point is that it is still not free of all impurities. For example, if fluoride came out, where will that fluoride go? I mean, that fluoride, if it is the HF, once I put water over here, the HF will dissolve. It will along with the phosphoric acid. So you need some steps to purify the acid. So the H2SO4, maybe you might get rid of the HF with that. Yeah, and the SiO2. So these two are being used to make H2SiF6. And then you can also put H2S from the top, because most of these rock phosphates also have arsenic. So arsenic sulfides have very low solubility. So you can make arsenic sulfide, and it can be removed from the phosphoric acid. So on the one hand, I can take care of my you can see fluoride here, H2SiF6. Okay, so I can actually then get rid of the impurities from this phosphoric acid, and the uranium etc. won't come, because typically what will happen is that it will go with the slag. Most of the rare earth, uranium etc. It's only the volatile stuff which will come here. And so finally you get a very pure acid. This is the acid that typically is used in beverages and detergent manufacture, which I told you. They don't necessarily use the wet process phosphoric acid. But then this would not be practical for fertilizer, because then the cost of fertilizer would be prohibitive. By the way, you can also make anhydrous P2O5 bone dry if you don't put it in water, or I can also react it with chlorine, as I told you, and I can make PCl3 and all. I mean, all the syntheses are not shown here. So this is really the overall process, which is the electric arc furnace method.
So I wanted to ask that the color of phosphorus, is it different due to the crystal lattice or the structure?
Yeah, that's a very good point. It obviously has a linkage with the electronic transitions in the solid state. I'll have to look at the electronic transitions, but it is mainly related to that. Yes, which in turn is related to the packing and everything.
So can you explain what the screening process is after the sintering?
After this one, huh?
Yes, sir. At the start of
This one, huh?
yes, sir.
Yeah. So what happens is that, what am I doing? I'm taking solids, right? I'm taking
Yes.
rock phosphate and I'm taking coke. Okay. And I'm, introducing air to heat it. Okay. And at the high temperatures, it will sinter. Okay. So when it sinters, I will get big particulate matter. Okay. Heavy stuff. But there will also be, all of it may not have sintered. So some amount of fines may still remain, okay, which will be very fluffy. And that you cannot introduce into your electric arc furnace. So the best thing is that you screen it. Screen it means obviously pass it through a sieve where the fines will get removed, and those will basically be put back over here. You understood? It's a mesh.
Yes, sir. Yes, sir. Got it.
Okay, got it, no?
Yes, sir.
So you can work it out over here. I might ask you questions, simple questions around these things. So you need sand, you need coke, you need carbon, because the electrode in a electric arc furnace is a consumable. It gets burnt. So you'll have to put in fresh electrodes. You need power, because the electric arc requires huge amount of power to generate that 1400 degree centigrade temperature. And then you need water. Okay, you saw that there are places to make phosphoric acid or to cool, etc. You need water. So this is what you require. Now just imagine, I need some 15 kilowatt hour per kg, means 15 units. And if you take something like 10 rupees a unit, you're talking about 150 rupees. So obviously phosphorus cannot be a very cheap material. And when you take into account all the other raw materials, etc., so it will be a much more expensive material. And if you try to make fertilizer with that, the subsidy on fertilizer would be massive. So you have to do ingenious things with the wet process itself, rather than saying that why don't I make fertilizer with the electric arc furnace process. And we'll continue on Friday. Okay, I will cover potash, which is the next process, and then I will move on to petrochemicals.